Hello there, this is Mr. Rodip, and in this video we will be studying about what linear regression is, so watching the equation and from practical examples. So let's begin. So linear regression, it is the foundation model, it is the foundation algorithm of machine learning. Okay, machine learning's foundation model is linear regression. What you can say is, so what is linear regression, LR? You can say that it is a supervised, it is a supervised machine learning algorithm. So I meant supervised, so I told supervised. What is supervised? Supervised means that you are giving an output column and there is an output here, output column here, and there is an input column. Okay, based on the input and output, the models learns based on the output. So let me give you a practical example. For example, you are studying for a test, okay, and you want to know, you want to know how many hours should I study for this test so that I can get 80 marks in that exam out of 100. Okay, you want to know how much hours you should study to get 80 marks. So what did you do? So you took a statistical measure. Okay, you asked your friends, what they had studied in the previous exam, how much they studied. Okay, it was a similar exam, so how did they study, how much did they study. Okay, some friends told that they studied for example 12 hours, and they got okay, it is the previous test. Okay, it was a similar test, so they got somewhere around 70 marks out of 100 hours, and this is marks. Some of your friends are told that they studied for 20 hours and they got somewhere around 80 marks. It can happen, right? And someone studied for 30 hours, they got approximately 90 marks. Okay, so this is the hours, this is the marks. See, the marks, the value is dependent on the hours they studied, right? If you study more, as you can see, you will get more marks. So what does it mean? See, marks is dependent variable, right? You can call it dependent variable, as it is dependent on hours. And you can call hours as independent variable, as it is not depending on anything. Okay, you were just asking your friends and they are telling hours, and then the hours is the is deducing the marks, right? This is how things are working on. You increase the number of hours and you get the marks also increased. You study for more hours, you will get more marks. All right. So what does machine learning do? Machine learning machine learning finds the patterns, finds the relationship between this input and this output column, and such that whenever you are curious about, if you study for a less hour, for 10 hours, how much will you get? Machine learning does that. Machine learning predicts this question marks. All right. If you study for 20 hours, if you study for 20 hours, it's already written. So for example, 25 hours. If you study for 25 hours, so how much will you get? Just like this. So also there is a term known as positive correlation and negative correlation. So what is positive correlation? See, on increasing hours, marks also increasing, right? This is positive correlation. And if somehow on increasing hours the marks decreased, right? If somehow, then it's called negative correlation. Okay. For example, the features, the input features. This is also known as the input feature. This input columns, The independent variables are known as input features, and this is not target column. All right. These are all the keywords required in machine learning. And when input feature increase, the value of input feature increase, the if the target column t decreases, okay, then you can say for sure that it is having negative correlation. All right. So the main question is, how will you predict from this to this? So what I told you, will be finding this relation. So how will you do that? So for this to save your day comes the famous simple linear equation, simple linear line equation. Okay, linear equation of straight line. Let me rephrase it. So save the day. Here comes equation of straight line. Straight line. What you have studied this in your childhood. So what does the equation is? Y equal to mx plus c. So why this mx plus c? So why this equation out of a sudden? All right. So if you start plotting this input hours to marks, you will find this like this. For 12 hours, it's you are getting 70, right? And for if someone's studied for 20 hours, they will get around 80. And if someone studies for 30 hours, they will get 90. All right. You can just plot more things like this. For example, if someone studied for around 5 hours, they will get around 40 or maybe. Again, so this is not a straight line. All right, this is not a straight line. They are close to straight line. So this is like a curve. Okay, it's a close to straight line. But why this straight line equation? So machine learning, what does this machine learning do? It predicts this line, okay, that almost represent the all the points. Okay, like this. It can be like this, right? It represents all the line. It doesn't need to be touching all the line to represent it. For example, we can't touch every line possible. Why can't it touch? Because it's a straight line, of course. How can it be touching like this? It will be a curve then. Okay. For example, the points are like this. Okay, maybe for some input and output, the points are like this, and you can't touch it, right? This will be like this. Okay, the error should be of minimum. Did I say about the error? The error need to be minimum. Why? See, there is an error, right? There is an error. So how can you say this is the line that the machine learning model draws? Okay, how this is the line that correctly represents all the points. How can you say that? And the line, and that line that correctly represent is known as best fit line. All right. How can you say that? So here comes something into the picture, that is mean squared error. Mean squared error. What is mean squared error? It is a distance. For example, this is a line, and this is all the actual points, and this is the line. So what is the mean squared error? This is this distance. You will draw this distance, and this distance, and this distance. And mean squared error is actually sigma Wait. So what is this y hat? So students, we are confusing things. What is sigma? How will I know it sigma is? So let me explain. So what is sigma? For example, sigma is denoting all the points. It's a summation of points. For example, this is the point of y1, and the prediction is called y hat. All right, y hat 1, and this line, this point is y hat 2. All right, the prediction is called y hat 2, and the line and the actual point is y2, and this is y3, and the prediction is called y hat 3. So what is the error here? Mean square error, ms error. What is this? It's like this. See, y hat minus y2 minus y2 hat. You can just replace things like this, because you are finding the distance and squaring things out. Okay. So why are you squaring things out? Because if somewhere you find negative, it can happen, right? If you take y2 minus y2, it will be negative, because y2 is greater. That's why you are squaring things out, so that none of them is negative, and then you will take. This is also correct, but to avoid confusion, I am putting the hat here. Right. So this is the ms error. So you are calculating this. This sigma means this. All right, and there is 1 by n. This is 1 by n. So what is 1 by n doing here out of a sudden? 1 by n is means you are finding the mean of things. All right, there are n points. There it will be n here it will be 3, right? And it will be 3, because there are 3 points in total. This is the formula of MSC. And so to find the best fit line, you have to play with two things. Remember, I said the straight line equation you already learned in your childhood. So what was that straight line equation? Equation of straight line. It's y equal to mx plus c. You can take, so m and c. What does m and c stands for? Okay, m is the slope. Okay, what slope? What is that? When c is the y intercept. What y intercept? What is that also? See, slope is the how much you change. This is the change. What change? How much y will change if you change x? Okay, this is the change. How much y will change if you change x. And what is y intercept? This is the offset. For example, if someone studies, this is our studied and this is the marks they got. If someone someone doesn't study, this is she or he doesn't study for the exam and she directly appeared the exam. Okay, then also you can't say he or she will be getting 0, because see, the exam might be easy, okay, and some pre existing knowledge can come into play, can help him or her, or he or she might cheat. So how to put that? So see, this will be, the graph will be like this. For our study he might get a marks of 30. It might happen, right? It might happen. If he might cheat, he or she might cheat, and then he or the exam might be super easy. It can happen like that. So this is the offset. Okay, even if the x is 0, there should be something to represent this fact, that even if he doesn't study, there should be some marks related to it. All right, did you all got it? And this is the y, this is the offset. Right? All right. So this is the slope. So how much, if you change x, how much y will be changed? So y, m and c. So how does m and c changes this line, which is our ultimate goal, to find out this line which correctly represents all the point. This is our ultimate goal. What, how m and C represents the line. On changing M, on changing M, you can see definitely changing M, you can definitely see that the line will rotate. Why am I telling that? See, slope means the change, how much will change. This is actually tan theta. Slope is tan theta, means this angle is indirectly denotes the angle. Okay, with the positive direction of x axis, with this direction of x axis, this is the angle. So on changing M, it will just rotate. So you can also understand by this, if you increase M, the rate will also increase, all right. So on changing, so this on changing this, it will also increase by many times, all right. See, this is the graph. If you this is the M, and on changing this, on changing x, this is increasing, all right. This is increasing. This is the increase. What is the increase? See, this is del y by del x, all right. This is slope, and if you just increase it, so the line will be like this. And on changing the C, for the same thing, for the same distance, it will be covering more of the part of the line, and that's why y will be changing more, all right. So it will be increasing more. So on changing M, what happens on changing M? Then you rotate the line. On decreasing M, you just rotate this side, and on increasing M, you rotate this side, all right. On changing M, just know that on changing M, you rotate the line. And what this on changing B does, or C, here is message C. That is a y intercept. Okay. So on changing the offset, you can just, it's like putting the line up and down, all right. If you increase the offset, it will be like this, the line will be like this if you increase the offset. So it's like putting the line up and down, right. On changing the y, puts the line up and down. So what is the conclusion from this? You have to adjust M, slope and intercept, to get the best fit line, to get the line that successfully represents all the point. This is the conclusion. So how will we get M and C for which the best fit line happens, best fit lines? So we will be using some algorithm here. Okay, we will be deducing things using some algorithm known as ordinary least square. We will be using that. Let's see what happens. See, y ordinary least square, ordinary least square. We will be using this to deduce the value of M and C. Before that, see, this is y equal to mx plus c line. More specifically, this is the y pred, all right. You have successfully predicted M and C, and you have to find this M and C, for example, if to get the best fit line, to get the Y prediction. All right, then how will you get the things? Let's just deduce things then. So from this equation you can see, you can get C equal to alright, it will be required later. So you have already found the error, right? So indirectly you have to decrease the error, decrease it to get the best fit line, right? Decrease it to get the best fit line. You have to decrease the error. So what was the error? You talked about mean square error. Okay, we talked about mean square error. So what was that? 1 by n. So how to find the value of C and M? So in your 11th 12th standard maths, you studied about something. So for example, let's see another thing. So let's say a concept. For example, if you draw the graph of x square, it looks like this. All right, it looks like this. So and the minima is here, right? This is the minima. How will you get the coordinates of the minima? How will you get? How will you get the coordinates? It's actually easy. For example, you will do it if f of x equal to y. If you do it like this, t f of x by x, and then you will get 2x, and if you equate 2x equal to 0 with, you have to equate it, then you will be getting x equal to 0, right? So this is 0, this is at 0, right, comma 0, this is x is 0 already, and if x is 0, you can find that f of x is also 0, then you will got the both the things x and y. So by this we will be calculating the minima, because you have to, at the end of the day, you have to minimize this, right? You have to find the minima and the m and c for which the minima happens. This is the equation. We have to find minima and m and c for which the equation happens, right? You have to do it like this. So how will you find out the value of c? See, this is x m comma c. The error is with respect to this, and this is then I comma 1, and this is n, and there is y minus y hat, and you can write this as like this also. Y hat is mx minus c, right? Here it will be y minus c. You did that, and then you have to find out the derivative del L del E m comma c with respect to c. We will be finding out respect to c. We will be finding c first. Let's see what is the answer. If you do derivative like this, so 1 by n, this will be treated as constant, so it will be coming outside. So here, so what it will be like this, it will be treating like this, and so the inside thing will be chain rule. So we will be doing chain rule here. For example, you have studied already. So let's take another example for chain rule. So to derivative this equation, so this derivative, so find out the derivative. You have to find out the derivative of the outside things. This is 2 x square plus 2 minus 1, because as you already know, 2 x to the power n a by dx is n x n and minus 1. All right. So you do it like this. Okay, and then you have to find the derivative of the inside portion, that is x square. Like this we get it. So let's proceed then. So what will be the inside thing? So this will be like this, and then the other variable will be treated as constant here. So the other variable here we are finding c. So other variable is m. We will be treating that as constant, and then we will be only taking this as minus 1, because derivative of a constant variable of only one variable will be treated as c, because there is a power here. So we will be taking this as for the derivative of this, and then we will be equating this to 0, because we have to find out the value of c for which the minima has been found. So this, I just put minus 1 in the right hand side. If you do it like this will happen, and just take this only. We have to take this, and then you can you can place 2 in the right side also. So place 2 on the right side, and then we can take like these things. Like this. As you can see, this is the average. This is the average. So you will be summing this and then divided by n, then n times. So this is the average, and then what is this? This is nm, right? This is nm, and this is the average. This is the average, and this is nm, because m plus m plus m plus m. This means m plus n times, right? And so this is the nm, and n could be cut. I will be writing this. N will be cut, and there will be m also, and this the nc by n, the same logics. C will be repeating n times, so nc by n is c, and just then and just calculate c equal to. So this is the answer. So this is the answer. All right. So this is the answer. So this is how you find c. So let's do the other thing next. So what is the other thing? We have to calculate the value of b, value of m, right? So let's at first write the equation, like the error m comma c, slope and intercept right in here. So what it will be, you already know it, y minus y hat, right? And then you can replace y hat with let us see, with mx plus c. So, what it will be, mx minus c, and then we can again replace c with this. So, too much replacement, alright, no issues with that. Let us replace w plus x bar. So, this is the equation we got, and we will be now derivative, apply derivative to this partial derivative with respect to m, right. Because we are finding m here. So, put 1 by n, this is constant. So, put this outside of derivative, mx, it will be mx bar, and apply the derivative here. So, put this and it will be like this, and then into it will be done. So, it's chain reaction, it's chain rule. So, we have to find the derivative of inside. So, we will be ignoring c, but there is no c always. So, we will be finding the derivative of this part, and this will be treated as constant, and this part. So, what is the what it should be? It will be like this, right? And we can equate this to 0. So, we will be equating this to 0, then take this to this side, it will be 0. And you can also simplify things by taking -1 common, and then what you can do, you can take 2 to the right hand side also, and then you can simplify things much more again, like y, like let us take common now. Okay, so we will be taking common right away, and here we can take minus m, right. We can take minus m also, they will say if it, and we can just multiply things here, x minus x bar, we are multiplying things. So, I can simplify things right now. Sigma 1, we can take this m constant outside of this, we can definitely do that. Okay, so you have put m outside of this, and then you can take this to right hand side, what it will be, and take m and put this thing to right hand side. So, this is answer you got for the value of m. So after doing this, you will be getting, so we will be getting the answer, that is so finding, after finding m with this formula and finding c with this formula, you will be getting the best fit line, and then plot it, we will be getting the best fit line such that the error will be minimum, right. So you got this equation. So let's write it in at 1 plus. So sorry, it will be b, it will be c. So c is y bar minus mx bar, and m is put it like this, and then you got the answer, you got c and you got m, right. For this you will be getting the best fit line after plotting. So this is a model. So whenever someone tells that they are training a model, so they are actually finding the value of the parameters. Here the parameters are m and c, right. So in machine learning terms, this m is known as weight, and this is bias. So at the end of the day, you are telling it, so how much weight the independent variable gives to the dependent variable, right. So how much weight the input feature gives to the output target column, right. So this is the bias is offset. So even if the 0 happens, even if the x is 0, there will be something in the y, right. If a student does not study, he or she might get some marks, right. This is bias. Okay, let's see the theory how a model is trained. Okay, so you have a data set, for example. So yes, at first you have a data set, for example some rows, some maybe 1000 rows or 100 rows, or it can be the score you got, the hours and the score or the grade they got, it can be 100. So you have to test the model, right. So how the model works, you have to test it. So there are data points, there are 100 data points, 100 student data, you have to test the model. So if it works or not, so you will be requiring extra data, but if you do not have extra data, so there is a smarter way of testing the model, that is just cut the data set in 70 to 30 ratio. 70% will be fed into the machine learning model, and 30% will be used to test the model, right, for training and for testing things out. For training data set, and this is known as training data set, and this is known as testing data set, and this is known as training data set, by the way. And then after, so how will you be testing the model? So there are various metrics, there is various metrics there to evaluate the model. We'll be talking about the metrics right now. Okay, so the first mean squared error. Okay, so you use mean square error here. So mean square errors now will be the metric for, would naturally be the metric for evaluating the model. Okay, so the formula is, you already know it. This is y pred, and this is mean absolute error. Then there is mean absolute error. So why is there mean absolute error? At first, let's talk about it. It will be like this, the formula. Instead of square, we are taking mean of things, uh, absolute of things actually. Okay, so instead of square, we are taking absolute of things. Okay, we are taking the modulus of this, we are finding the absolute value. So why this to this? Okay, so see, as you can see, in square there is square, so the metric is not in the same unit as the input variables, right, as the output variable as the input variable. It's a squared unit. So that's why main absolute error was introduced. So put things in the same unit. But there is also issue with mean absolute error, that is, it's not differentiable, because you are differentiating things, right. So it's not differentiable, at 0, at 0 some other value differentiable, because you know the graph of modulus, it happens like this. It's not differentiable at some point, it's not differentiable, right. So that's mean absolute error. It has already drawback. So there is another, there is root mean square error, and instead of, as you might have guessed it, instead of modulus, instead of square, you take, instead you put things square here, but you take this root square to MSC, root mean square error. So the benefit of this is, it is actually returns this in the same unit, in the same unit. Okay, these three are the metrics to evaluate the model, and there are two more metrics, and the metrics will be depending. So what metrics to use, it will be dependent on the data set. You might use all three of them and see what works or what works not. And then there is the fourth one, which is R square, R2 score. R2 score. Okay, this is R2 score. So as you can see that these three errors, are not, you cannot compare for one model to another model. This is absolute sense. How do I mean by absolute sense? So you cannot see the percentage of things. For example, 100% means there is no error, okay, and there is 80%. You can see like that. See, you cannot compare between models. So it's because it's not absolute. You cannot see, cannot bound it within a limit. For example, 80%, you cannot do it like this. 80%, you cannot find it. See, 80% the model is correct. You cannot do it like this. Then that's why R2 score is here to give a absolute sense, to, so that you can compare the models among your friends. Okay, so everyone applied different algorithms or different data sets, and then they can just compare things with the score. That it will give you a more absolute sense and more meaningful, it will give you a more meaningful way to represent the error. So what is R2 score? Let's talk it. It is sum of squared error, okay, sum of squared error of the regression line and sum of square error of the mean line. What do I mean by regression mean line? Obviously you know the regression line, right. So for example, this is the model, this is the, for example, this is the graph of grade, and the LPA or placement. Okay, the lakh per annum. This is the placement. This is the placement data. Based on grade, every student has secured some amount of placement, some amount of, for example, for grade 8, so 9 LP job she or he has cracked, like this. So whatever, what say someone wants to admit to your college and she or he asked you about what is the placement, what is the placement report. So how many of what is the probability of her getting a job or not. So how, what will you tell? You, based on the 100 data, based on the past 100 data, how many of them, what is the average LPA, you will tell it like this, right? You will be just do it, see, here is the average. So 8.5 may be the average, you are saying that see the average data is 8.5, okay, 8.5. So if a student has graduated, he or she has graduated with a 8.5 LPA job, right? So you are telling just like this. But if you take grade into consideration, if you take grade into consideration, then the data will be different, then there will be building a model. So how much it will be dependent on the grade axis as well. So instead of you tell her in a proper way, based on grade, based on how much grade has she or got, he or she is getting this much LPA. You can say it like this by building the regression model. Okay. Yeah, so you can say it like this. If you get 9 LPA, 9 grade, if you maintain 9 CGPA in our college, you will be getting for example 10 LPA, instead of just telling out the average, instead of telling out her that our average placement report is 8.5. Okay, you can just add more information to it. Okay, to see mean. So the less information one is, so the easiest way is to just do things mean, just calculate the mean and just say her that this is the 8.5 is the average placement, average LPA. But if you want to add more information, you can add grade. You can tell her, if any student has got 9 CGPA, he has cracked a 9 LPA job. So you can, if you can maintain it, you will be able to crack 9 LPA job. You can tell her that we can add more information to it. It will be a better model, right? It will be a better model. So this is the mean. This is the easiest way. So it doesn't add any information, just telling the mean of things, and this is the regression line. It is adding the more information. You are telling, you are able to tell that if you get 9 LPA, then you will be able to get, if you maintain 9 grade in total semesters, and you will be able to get a 10 LPA job. You will be able to tell her that, right? So this is the mean, this is the regression. So that's how R2 score works. It's like this. This is the mean. Okay, this is the R2 score. You can see this is the R2 score. So for example, if our model gives 80%, 0.8, okay, we may tell that this model is doing good after all, because it's closer to 1. So what happens if R2 score is 1? What happens like this? Say if R2 score, then the model is not making any error, model is perfect. The model is perfect. It's like, see, y is equal to y hat, that's why it's 0, right? That's why it's 0, because it's calculating 0, there is no error here. Then the R2 score, it's more likely the model is overfitting. So what is overfitting? I haven't talked about overfitting yet. Okay, it's like the model memorize the information. Okay, like the model memorize the information, and when he or she when the model just gets new information from unseen data when it's told to just predict things, it perform ORs because it has memorized the information. That's how overfitting works. Overfitting, I will be discussing more about overfitting, and then there is underfitting also. Then the training doesn't happen too good, that's called, the training itself doesn't happen too good, that's underfitting. And then if R2 score, if R2 score is 0, how can it happen? So the model is not good. So the how can it happen? So this is equal to this. So the model is basically the mean, and that's why it's 1, and therefore 1 minus 1 is 0. The model is bad. The model is mad. Yeah, model is mad. Right. The model is bad. And what if the R score is negative? It can happen, right? The model is worse in that case, because in that case you have the mean is greater than this. The model is performing worse than the mean also. It can happen the model is like this, like this. You have the model is here like this. So it's performing worse than the mean. First of all, the mean in here it is performing worse than mean. It's about, can't predict anything seriously. That's why the it's negative. So therefore the model is worse, right? So how can you say the model is performing good if your R2 score is more than 0.5, closer to 1? If your model is closer to 1, not 1, if your model is closer to 1, you can say the model is good. It's closer to 1, you can say the model is good, the model is good, then you can say that. So I have talked about something overfitting and underfitting. What is that? I'll be giving a brief introduction to this. So overfitting happens when the line just pass through every point. It doesn't generalized. It doesn't generalize the points. It just pass to every point possible. For example, this point, this point. So we are learning about linear regression. Okay, we will have polynomial regression in the future. So in polynomial regression, it can pass straight line can't pass to every point because it's a straight line, of course. But polynomial regression will be able to pass to every point because it's about it's drawing the polynomial, right? It can form like this also. It can form curves. That's why it's able to pass every line. It's not generalizing because it has just memorized the information, memorize the points, memorize. The generalized line would be like this, because it has memorized the points. For example, if you have been told to tell what will be the value, here, okay, what will be the value of here, you have been told to, you have been given a query, but our model, our overfitted model will tell this, but the actual the error will be less in generalized model. That's it, the error is much more. In underfitting, the model is not trained properly in itself. The training the model is not trained. We didn't find the value of W and bias here properly, weight and bias or slope and intercept, whatever you call. The model isn't trained properly. You can call that as underfitting. Right, you can say that. So then overfitting, you understood the brief introduction of overfitting and underfitting. We will be talking about more in the upcoming videos. So what about, so I mentioned there is another one matrix, right? There is R2 score and there is adjusted R2 score. And there is adjusted R2 score. So why adjusted? Why do you require adjusted R2 score? First in R2 score, it can happen. See, in R2 score there is some drawback. If you add some irrelevant feature, right? If you add some irrelevant feature in R2 score, the R2 score will value may increase or may even remain at the same point. Okay, same. it may remain same. Okay, if you add, more irrelevant column, but we haven't talked about multiple features yet, but still I am including this because we will be covering out polynomial regression in later videos, where we will be seeing about how multiple features influence the model, right. We will be predicting the other things as well. We will be predicting a model on that case also. If you add more irrelevant features, irrelevant features, the R2 score may remain same or may decrease or may increase, right. It should have been decreased, but it is increasing. Okay, it's telling that see your model is getting accurate, but it's irrelevant, right. For example, for hours, number of hours studied, you are predicting hours versus the score you got, right, the score you got. And you may add another feature, this is what is the weather today, how much is the temperature, how much is the temperature and outside. So temperature by nature doesn't affect the score. It can affect if he or she just drops out if there is more temperature. Just joking, but directly it will not have any impact on score, right. Temperature will not have any impact on score. So it's irrelevant, but the R2 score might increase or remain same, but it should decrease. That's why adjusted R2 score came into the picture. Okay, so what is the formula of adjusted R square? Adjusted R square, R2 square, R2 score adjusted. So what is the formula of adjusted R2 score precisely? So adjusted R2 score is 1 minus, here it is 1 minus R2 score, the normal R2 score, and then here it is n minus 1, alright, and here it will be n minus 1 minus k. So what is n, what is k? N is the number of data points or row, you can say, and k is the number of input features. And so you can see, if you increase, if you add irrelevant features, on adding irrelevant features, on adding irrelevant feature, what will happen? K will increase, and R2 score might increase, but it will be increased by a bit, right, or may remain same. But if k will increase, overall it is going to decrease, right. Overall it is going to decrease because n is fixed, and n minus k, it will k will be less, right, k will be less and it will be overall decreased, but it will be decreasing more than this. It will also decrease 1 minus R square, because it is increasing, overall it will decrease numerator. So ultimately the decrease will be more in case of denominator. So what will happen as a result? For example, this term is 1 by 4. So if it is, the decrease is more, then 1 by 4 will become 1 might same, 1 numerator might remain same or it might decrease, but still I am remaining it same. So 1 by 4 will be decreased to 1 by 2, right. So if you do this like this, 1, so if you calculate a total thing, 1 by 4, it will be 1 minus 1 by 2. So what will be the answer? See, 0.75, it will overall decrease, right. So ultimately it is decreasing. Decreasing, which is a plus, which you need, right, because on adding irrelevant features, at least it should not be increasing. So that's why you are using adjusted R square. But on adding relevant features, how it's increasing? Let's see that. How it's increasing? How it's increasing? Let's see. So, on adding irrelevant features, see, R2 score will be increasing many more times. So the numerator, the decrease in numerator will be more in this case, because R2 score will be increasing, and if R2 score is increased, then the overall decrease will be more than the denominator. It will be the case, decrease in numerator will be greater than decrease in denominator, and ultimately what will happen? Ultimately, this term, the ultimate thing will be the overall term will increase, right? So it will happen like this: 1 minus 1 by 4, 1 minus, it will be like this, 1 minus 0 1 minus 2 by 4, let us call it 2 by 4, and then it will be decreased to 1 minus 1 by 4, right? The decrease will be more, and you can calculate things from here. It will be 0.5 to 1 minus 0.25. Right. I am taking the denominator as constant only, because I am not changing it, because the decrease is very less, because the numerator is increasing by many times, that is why I am doing this. So, 0.1 will be increased to 0.75, it will happen like this. Okay, this is the thing, overall increase, and here overall decreasing. So, I guess you got the things of linear regression, how it is linear regression, how do you find the value of slope and bias. Okay, weight and bias, how do you get the value of weight and bias, for which you get the best fit line. Then we discussed about overfitting and underfitting. Then we discussed about what is training data and what is test data. And then for test data, we discussed about the various metrics involved for testing the model. There is 5 metrics in total, as you can see: MSE, MAE, RMSE, R2 square, adjusted R square. And that is it for this video. In the next video, we will be implementing linear regression more in practical in Kaggle, using a simple data set. We will be writing code. We will be writing code of dividing the data set into train data and test data. We will be also training the model, and we will be predicting, and we will be calculating the R2 score, the adjusted R2 score, the MSC, MAE, and much more. Thanks for watching. Bye for now.